This is the screencast for section 7.3, example 4, finding volumes using cylindrical shells. So in this example, it says the region bounded by the curve y equals square root x, the x-axis here, and the line x equals 4, so this like curvy triangle piece, is revolved about the x-axis to generate a solid. Now, before example 4, we would probably just use the disk method. There's no hole in the middle, it's getting rotated around, that's not that difficult. But now we're going to find the volume of the solid using cylindrical shells. So the question is, what does that look like? Well, we're going to take the side of a cylindrical shell and we're going to rotate it around the x-axis. So you get this series of cylinders. Now, of course, the more cylinders we put into this object, the more and more you're going to see it look like a solid object. Looks like a Jell-O mold, I guess. So all these little shells are going to be stacked inside of each other, kind of like soup cans. They just get stacked inside of each other. So our cross section this time is not simply a slice across. It's not just a cut across. It is a shell, a cylindrical shell. So what we're going to be doing is we're going to be not rotating around the y-axis like this, but picture the original area. We're going to have shells whose edges run horizontally. So we're going to be rotating them around the x-axis. So ours is going to look more like this type of an object. And we're going to stack the shells inside so that they're kind of rolling around on the countertop, if you will. So first, let's try and draw our own 3D picture of this, pretending like the book didn't give us this beautiful one. I'm going to draw an edge of one of my shells underneath, so opposite the x-axis, opposite the axis of rotation. Then I know that this is going to rotate around, so I can see, if I draw circles, what that rotation would look like. So here is a cylindrical shell, no top, no bottom, just the shell on the outside. And yeah, the book did a great job. Wonderful. So since the cross section is a cylindrical shell, the area of that is going to be 2 pi r times h. So the circumference of the cylinder times the height. So now we have to find out what the radius is. Well, as you can see, the distance of the radius here is just the y-coordinate. So the radius is going to be y. Because remember, we're integrating with respect to y, so we want this in terms of y. That's just the y-coordinate, the height. Now, the height, not of the curve this time, but of the actual cylinder, is going to be the distance all the way out to the edge here, the base, I guess, of this cylinder. So 4 minus the distance from the y-axis to the curve. So in that case, it's going to be 4 minus y squared, a total length of 4 minus the distance from the y-axis to the curve, y squared. So minus the x-coordinate, which is expressed in y's y squared. Alright, well now we can find the volume. We're going to integrate from 0 to 2. That's because the edge of our cylinders are going to be stacked from the middle 0 all the way to the outside to 2 on the y-axis, 0 to 2. The surface area of our cylinder is 2 pi y times 4 minus y squared, so 2 pi times the radius, the y-coordinate, times the height, 4 minus the x-coordinate, which in terms of y is y squared. Give each of those cylinders a little bit of thickness, a dy, and now we can integrate and we get 8 pi cubic units. The now try problem number 33 says use the cylindrical shell method to find the volume of the solid generated by revolving the shaded region about the indicated axis. In this case, it will be the x-axis. So again, our shells are going to be rotated around the x-axis, meaning their open lids are going to be a hole around the x-axis and a hole around the x-axis over here. So I got to draw those. So I'm going to pick an edge of one shell in the curve and draw the other edge opposite the x-axis. Then I'll connect those two with the circular motion, the open top and the open bottom of the shell. So I can definitely see that the cross-section that I'll have to find the area of is a cylindrical shell. The area formula for that is 2 pi rh, so the circumference times the height of the shell. So then, if I have this simulation over here of a shell, I can see where the radius is coming from. I can see that the radius is the distance from the x-axis to the curve, which is just the y-coordinate. Remember, it would be an expression of x, but we're not using dx in these problems, we're using dy. The thickness of this shell is a little change on the y-axis, so all I need is the y-coordinate for the radius. The height, however, is going to be the distance from the y-axis out to the curve, so the x-coordinate, and by definition x equals 12y squared minus y cubed. So now I have the radius and I have the height, so the area is going to be 2 pi times y, the radius, times the height, the x-coordinate in terms of y, of course. So I'm going to simplify a little bit to make my integral easier. The volume then is going to be all these cylindrical shells within each other, so all these cans stacked inside of each other, and the edge of these cylinders is going to stretch from 0 out to 1. Now, yeah, it's going to go from 0 to -1 on the other side, but one shell will only go from out to 0 to 1. We don't want to double the number of shells by going to -1. One edge of one shell, if we stick with the same edge, is going to be stacked from 0 out to 1. So that means the area of the shell, we found that formula. We're going to give each shell a little thickness, dy, integrate, and I get 6/5 pi cubic units.